Hello everyone. Welcome to another discussion dynamics. Today we will continue. Kinetics of particles. We will focus on kinetics in curvilinear coordinate systems. But before that happens, let us look very quickly on the info session. So I think that on Monday we have our first midterm, right? Yeah, it's not a first midterm in your life. You know what to do. You know how to get ready for it. I'm not going to like reinvent the wheel with saying you all the details. However, might be one detail. Homework for is ungraded. However, I strongly recommend that you guys solve these problems. Okay, just treat it as a practice before the competition. Yeah, and you're on Monday you compete against us, against me and other teams. Yeah, so just make sure that you came there prepared. Okay, and material covered today is related to questions 1 to 5 on that homework. Okay, and material covered on Friday, this coming Friday, is covering questions 6 to 8. All right, and these guys, practice makes progress, no solutions manual. All righty. On that video I recorded on Sunday, and I shared it with you on Sunday. Excuse me. I think I finished with this sentence, yes, that with this promise that at the beginning of this discussion we will have a brief Q&A on that question 2 from Friday. Mike is yours. Any questions? Everything was clear in there? Or do you have any questions? Would you like me to clarify something very briefly? No questions, yes? Okay, John?
I don't have a question about
how about Piazza? And how about office hours? Yeah. The reason for that is that we might run out of time. This is first reason. Second reason, I have no idea how quizzes look like. Okay. The only thing I know how look like, I'm responsible for discussions and exams. Okay. Quizzes is not my business. Okay, this semester. But office hours, come to my office hours. I will answer the question with a smile on my face. No problem. Yeah. Or Piazza. Okay. So that was quick, that was fast. So today we'll do 2 examples. Example number 1, kinetics in NT, and example number 2, kinetics in R theta. Ready? Let's do it. Please familiarize yourself with example number 1 before we start our solution. Okay, so what do we have in here? Look, they provided us a beautiful drawing here. Yeah, this is I believe isometric view. Yeah, this is isometric view. Yeah, isometric view. And at home, I just decided to redraw it in a side view here. Yeah, this is a side view of that thing. So what do we have in here? We have this construction rotating. Yeah, this is rotating, and we have a collar D that is in here, and that collar has a mass. We have some friction between collar and the rod. We are on Earth, so we have gravity, and they told us to find this velocity, yes, velocity of this collar, so that collar does not slide at all. Yep. You guys, I hope guys that you know that if this velocity is too small, that collar will start sliding this way. Yeah. If the velocity is too small, that collar will start sliding this way. However, if this velocity is too large, that collar will start. The centrifugal force will be larger than the force coming from gravity, right? So that collar will start sliding up the incline. Okay. Any questions about that? No. Okay, so we know the weight of the color. We know this radius that is not on the picture. This radius. We know this radius. We know geometry. We know the incline. We know coefficient of static friction, and we know that omega is constant. Okay, and they ask us to find basically that range, V mean and V max, such that color does not slide. Such that color does not slide. Okay, solution. It's not going to be a big surprise for you guys. We will start with FBD. FBD, and we will prevent sliding down, okay? Prevent sliding down. And in here we will have KD. Okay, so let's model our color as such particle, and that particle is represented here with this rectangle. Okay? Two exactly the same drawings. Two exactly the same drawings here and here. Okay, so what forces act on our system? This is alpha and this is alpha, by the way. So I will start, okay? We have mg. Any other forces act on our color? Anybody wanna say something? Friction, yes, exactly. And which direction? We wanna prevent sliding down. So it will be acting exactly you're showing, right, Isabella? This way, TF. Yeah. There is one more force acting on the color, Kyle? Perfect. Perfect. Okay. So it will be this one. Normal force. Okay, I don't want to do it with R. Wait a second. This will be R1. And I think that there is one more force acting on that system. Kyle, you can repeat what you said. Exactly, because that normal force will have two components. Do you see it? The other component will be here. I call it RT. Okay, the other component of that force is going to point outside of the board. It's going to point towards you guys. Do you see it? Yeah. Okay, now let's choose coordinate system to express our motion in. I decided to choose anti-coordinate system. At home, you can do it at home. You can do it in R theta if you want to. Okay? But I choose anti. So I think that since our velocity is pointing this way, yeah, this is our velocity. Don't draw it, okay? Don't draw it. Our velocity is pointing this way, yeah. So I decided to put ut in this way as well. Ut is always aligned with velocity, yes. So that means that un will be pointing this way, and this is our k direction. Okay, so that means that we will have MAT, we will have MAN, and we will have MAZ, surprisingly, yeah? So these are three positive directions we are going to express our motion in. Okay, what's the next step? EOM, yeah? By the way, this is the recipe to solve these problems. FBD, EOM, and then we will see what next. If you follow that recipe, you will solve every problem in kinetics. Yes, Jason? Yes, yes, yes. Sum of forces along the t direction. And this is our positive direction. Yeah. So in here, I believe that we have only one force acting there, yeah? We have only RT, and this is equal to MAT. That's it, yeah? Now, sum of forces in the n direction, and I believe that we decided that this is positive direction, right? So what do we have in here? Oh no, we have to do some projections, yes? Okay, let's do it quickly. RT will be here. Let's do orange. So I wanna project this guy here, okay, on these two components. So if alpha is in here, I believe that alpha will be also here. No, alpha won't be here. Alpha 90. No, of course not. Alpha will be here. Sorry, guys. Alpha will be here. So this one will be R1 sine or cosine? Which one? Yes, you didn't. Come on, man! You must know. You must learn that. R1 sine theta. Yeah, guys, make sure that you know which one is sine and which one is cosine. Okay, it's high time to learn it. Okay, it's high time. Okay. Open your notes from middle school, right? Maybe yes. Okay. If alpha is here, alpha will be here as well. So I believe that this one will be TF sine or cosine. This one. This one will be sine. But wait a second. Okay, I usually say take another guess. But okay, this one will be cosine. Sine. Yeah. Sine alpha, and this is TF cosine. Yeah. Yeah. You said correctly, yes or no? No, I already forgot. Okay, that's good. So now we are ready to write the equation of motion for n direction. So I believe that R1 cosine alpha points in the positive direction, and TF sine alpha points in a negative direction. And this will be equal to MAN. And now FZ, with this positive direction, we have R1 sine alpha plus TF cosine alpha, and we have also negative mg. And this will be equal to MAZ. Okay. I like when these guys are aligned. Yeah. Okay, so we are done with our equations of motion. However, you guys should recall that A can be expressed always in such coordinates: AT UT plus AN UN, right? And just to remind you that AT is equal to dV dt, and AN is equal to V squared over rho. Okay? So, you guys maybe can already tell me that this is 0, right? Because V is constant. Yeah, they told us, I think even in the problem statement, that V is constant. So that simplifies the problem because this is 0. Okay? And we already can see that RT will be, that reaction force will be also 0. Great. First information we figure out. Okay, now what is rho? Can any of you tell me what is rho? That radius of curvature, if I scroll up the picture. Exactly, it will be 2 feet. Yeah. So instead of rho, I will just write lowercase r. Okay. So rho, it's r. And we know what r is. 2 feet. Great. So this will be v squared over r. Great. And by the way, as a digression, what is AZ? Why? You said it right. And you said it. Yeah. Why is it 0? Exactly. In other words, it is spinning around. Yes. Our color cannot leave this plane. Yeah. Yeah. So it does not accelerate this way. It does not accelerate this way. Exactly. Yes. Perfect. So this will be also 0. So this also will be 0. I'm just going to, I like to write comments, okay? So I'm just going to write this comment. The color does not slide. Does not slide. It cannot leave the horizontal plane. Cannot leave horizontal plane. Okay, great. And we are just going to plug this information here. Okay, so instead of MAN, we will write MV squared over R. Okay, let us recap all of these equations. So we'll have 0 here, we'll have mv squared over r here, and 0 in here. Okay, so how many equations do we have, and how many? So we have 2 equations, right? We see that the first equation does not. We can leave alone, yeah. So we have 2 equations, and how many unknowns? I believe that R1 is unknown. I believe that TF is unknown. And I believe that V is unknown, yeah? Dang. So we have 3 unknowns. Okay, where can we find the third equation? Proposition? Friction, yes. We have a static friction case. Static friction case, where TF is lower or equal mu s n. Okay, n is a normal force. And by the way, in our case, normal force, so n is a normal force. In this case, n is equal to r1 squared plus rt squared. Yep. However, rt is 0. Yeah, you can see this equation, for example. Yeah. So our n will be equal to r1, basically. Yes, Will?
How do you know that that's what n is equal to?
Oh, that's simple. Just if you look at this picture here. This is reaction force.
Oh, okay.
Yeah.
So it's a negative reaction force.
Of course, yes, of course, yeah. Yeah. That reaction force has 2 components, yes? One pointing this way, the other one pointing this way, yeah? So this way and this way, yeah? So it will go somewhere here, yeah? However, the green vector is 0, yeah? Good question. Thank you. Okay, and we are not going to use that inequality, right? Because they ask us to go for extreme value of v. Yeah, v extreme for TF max. Yeah, equals to mu Sn. Yeah, they ask us to go either for v mean or v max. So the extreme value will be right at the sliding. Yes. So we're not going to go for inequality, but we are going to go for equality. Okay, and we are done. Yeah, we found our third equation. So let me put it here. Let me write this one here as well. So TF is equal to mu S R1. Okay. So these are three equations, three unknowns. You guys know how to solve it. I am not going to solve it with you. I'm just going to give you answer. Okay. So this is equation number one, equation number two, equation number three. If you do a little bit of algebra to equation number two, you will end up with R1 equal to sine alpha in the denominator plus mu s cosine alpha mg. Okay, and if you plug in values, you will obtain that this is equal to approximately 0.5489 pounds. Okay, and now from equation number one, oh, I forgot about squaring here. Check this out. Yeah, from equation number one, you will obtain that v extreme is equal to plus minus square root of r divided by m, r1 cosine alpha minus mu s sine alpha. Okay, plug in values. V extreme is equal to plus minus 2, 0.5 divided by 32.2, 0.5489. I'm just plugging in values. Cosine 40 degrees minus 0.35 sine 40 degrees. Grab your calculators and obtain that V extreme is equal to plus minus 6.1849 feet per second. By the way, V extreme points in this direction. Obviously, like it has no other choice. It has to point in this direction. Yes. Okay, this is minimal value, yes, because we were preventing sliding down. Do you remember? So V mean is equal to plus minus 6.1849 feet per second. V minimal. Okay, that's it. This is the 50% of the problem done. 50%. Questions? Jason?
I missed earlier. How did you say you got n square root r1 square root plus r2 squared?
Sure. This is normal force between the rod and collar. Okay, do you see here? Do you see blue vector and green vector? Do you see it? So our normal force has two components, right? And n is magnitude of this vector. So this is how we take magnitude of a vector, right? We squared each component, sum them up, and we take a square root. This is the magnitude of vector.
So what is RT?
RT is pointing towards your eyes, towards you, in your eye, exactly. Anna, yeah.
R2 0 because it like can
RT is 0 because it does not, this value is 0. This value is 0 here. So our thing does not accelerate. Yes. Yeah, that's why that reaction force is 0. Okay? That's why. This equation, look, this equation. Any other question? Okay, let's find Vmax. So Vmax will be found in a very analogical way. Okay? We're gonna spend like not more than 5 minutes on it. Okay? Now, Vmax. So again, guys, we're gonna draw FBD and KD. So I'm going to copy them. Okay? Just to save some time. I love that I can copy those pictures. You know that before I was using, I know that you don't like it, but I like it, yeah, because you probably prefer me to write everything on the board, yes, so that you have enough time to write it in your notebooks. However, I love that I can copy things because I don't have to like redraw it and so on. Okay, guys, so there will be only one change between what happened earlier and what will happen right now. Okay, so far we found V mean, and right now we just would like to find V max. So only one force will flip. Which one? John? Exactly, yeah. So friction will be pointing the different way, yeah, the other way. So friction will be pointing this way right now. Exactly, and everything else is the same. Okay, everything else is the same. So you guys can again project these forces here and here. Alpha was here, so that would be R cosine alpha, R1 sine alpha, and now our TF. I'm just gonna move mg somewhere else. Okay, I'll move mg here, and now this TF. So if alpha is here, alpha will be here, right? So this will be TF sine, and this will be TF cosine alpha. Okay, that's the only difference. That's the only difference, okay? So please don't hate me, but I will just copy paste our equation of self motion as well. By the way, this will be on YouTube. So I think I can maybe even, let's do everything. I'm gonna copy paste these equations of motion. All right, so and the only thing that will change here is just sign of TF. So we don't have minus TF here, but we will have plus. Okay, we won't have minus TF cosine alpha, we will have minus. This is the only difference. Okay? And again, you guys told me that this is 0, this will still be 0. You guys told me that this will be V squared over R. It will still be V squared over R, and this there will again be 0. Okay. And again, we have static friction case. Static friction. TF lower equal mu Sn. So our TF max for V extreme will obtain TF max equal to mu S R1 again. Okay, and we end up again with two equations with two unknowns. Here, we end up with this again. So I'm just going to flip these signs. This will be plus, this will be minus. And okay, find R1. R1 will be exactly the same quantity. Just instead of plus in here, there will be minus. Do it at home. Yeah, there's no sense that I'm gonna do it with you in here. Yeah, just minus here. Okay, grab your calculators and plug in values, and you will obtain that this is approximately 1.3345 pounds. Okay, and now our V extreme will be exactly the same value again, with one caveat, and you already know what that will be. Instead of minus here, we will have plus in here. Plus. Okay. Grab your calculators and obtain that our V extreme will be approximately plus minus 13.0514 feet per second. Okay, this is our Vmax. And this is our solution, yeah. Answer? V belongs to 6.1849, 13.0514 feet per second. This is our range of V to prevent sliding. Questions? I have one question. Why do we have plus minus here? And what does this mean physically? Exactly. It can rotate either this way or the other way. Perfect. Yeah. Okay, guys. Honest question. Do you hate me that I copy paste? A little bit, at least? Please. Okay, Tom, this is your last discussion here. You're not allowed here on Friday. No, I'm kidding. Sorry, but do you really prefer me to again repeat the same sentences? You will fall asleep in here. Yeah. So just you have notes already at home. Just rewrite everything, or if you want to. You don't have to. Nobody to tell you that. Yeah. And just replace that little minus with a little plus. Okay, that's it. I just want to sell a concept here. Okay. So part B, part A. What's the difference? Friction flips. Okay. Questions or example number 2? Cool. Thank you, guys. Thank you to be so understanding. Yeah. We have only 50 minutes. Yeah, I can stay here longer, but you cannot. Yes. So let's do that copy pasting maybe more often even. Okay. Please familiarize yourself with the problem statement before we start our solution. Can I have an attendance list? Yeah. I can approach them. Everybody? How about Paul? Paul Nielsen? Only Paul. Okay, and Calvin, are you here? We have one new student that said that he will come here. Okay, Calvin, you're not here. Okay, so what do we have in here? We have such construction. And I think that this is even isometric view, but we can use it as a side view. It's a good enough side view for us, okay? So what do we know? We know that mass is here, yeah, and mass is on that rod. There's no friction, by the way, right now. No friction between rod and the mass, but the role of friction is going to be played by this tension in the cable, okay? This will be our kind of friction, okay? What else do we have? We have thing that rotates in such fashion, and we also know that this winch rotates with lowercase omega, yeah, and that winch has radius b. They ask us to express tension in that cable as a function of time, And they also ask us to express reaction force between collar and the rod, so this vector, as a function of time as well. Okay, questions? I'm not going to surprise you guys. FBD. Okay, and KD, of course. So we are going to represent our particle as this rectangle. Okay, and let's express it in this coordinate system. This time, polar coordinate system, okay? Polar coords. So r theta. So we will have, I believe, you are pointing this way. Yeah, because our position, I would like to place, by the way, let me scroll up the board. I will place this coordinate system here, okay? So that would be UR. Yeah, because do you remember, UR is always aligned with R, with the position vector, yeah? So our R will be here, this green vector. So that's why UR is here. So if UR is here, U theta will be pointing this way, inside into the board, okay? And K is old good K, okay? Okay. So U theta will be pointing into the board. Oh, sorry guys, not UT, U theta, yes. U theta. And K will be pointing up. Okay, so what forces act on our thing? I like easy questions and easy answers. So I'm gonna start mg. And what other forces act on our thing? Already mentioned tension in the cable. And normal force, which again has two components, yes? So we have Rz and R theta. Normal force again has two components. Okay, we are done with our FBD. Now, kinetic diagram. Let's show all the inertia forces acting on our particle, which is easy after you define the coordinate system. UR, U theta, and K. Okay, so I believe that we will assume that this is positive direction, MAR, MAZ, and this will be MA theta. Great, we are done with FBD and KD. Any questions to what happened so far? I have a strange feeling that I'm talking too fast, guys. Have I lost you today a little bit? No, everything is fine, yes? Yeah, nobody's looking at my eyes besides you, sir. Yeah, okay, sorry. Okay, second part, EOM. Of course, not third part, but second part. Second part, EOM. Okay, sum of forces in the R direction, and this is positive direction. So in here we have just minus T, yeah? Minus T is equal to MAR. Now, sum of forces in the theta direction. This is positive direction of theta. So in here we have only R theta. Yes. And this is equal to MA theta. Now, sum of forces in the Z direction, with this direction as our positive direction. So in here we have RZ minus MG, and this is equal to MAZ. Sir, I forgot your name. What's your name? Hamilton? Yes. What is AZ? Perfect. For the same reason. For the same reason, yes. Our color cannot leave the horizontal plane. I think I never asked you for your name. Yeah, yeah. Sorry. So RZ, we already know that RZ will be mg always. Great. Okay, that's it when it comes to equations of motion. Yes, I just look at this. By the way, I'm going to repeat it exactly. I'm going to repeat exactly the same what I said on Wednesday. These two drawings and these equations, yeah, have something in common. Yes, we must build these equations based on these drawings. Yes, I know that most of you understand it. Yeah, I just based on the past experience, I just want to point it out. Okay. Now recall that our A can be always expressed as AR UR plus A theta U theta, right? Where AR, if I remember correctly, was R double dot minus R theta dot squared, and A theta is Coriolis acceleration plus this, right? Okay, and we will basically plug this value here and this value here. Okay, but before that, let's maybe simplify it. Okay, so guys, can you please tell me what is R dot, and R double dot? And also what is theta dot and theta double dot? Based on this picture, based on what they told us. Okay, what is theta dot? Let's start from easy things. What is theta dot? Omega, but lower or lowercase or uppercase? Uppercase, perfect. And this is constant. So I don't even dare to ask you what is theta double dot, yes, because you will leave the room probably, yes, it's 0. Yeah, okay. How about this value? R dot. In other words, if this is R, what is the rate of change of this R? What is this velocity? You can speak up. Omega b, perfect, yeah. And lowercase omega, yeah? Omega b. And this is also constant. Yeah? So I don't, this is 0. Yeah, if R dot is constant, this is 0. And if we integrate R dot, we'll end up with something like that. Omega b t, no, different, sorry. L0 minus omega b t. Yep, this is our expression for R. R is a function of time. Okay, so now we can see that our AR is going to be minus L0 minus omega bt omega square, and A theta will be 2 omega b omega. That's all. That's it. Yeah. Now plug this in our equation of motion. Okay, so I hope, guys, that you don't mind if I copy. I'm going to copy these equations. Yeah, these are our equations of motion. But instead of AR, I'm just going to plug this one. And instead of A theta, I'm just going to plug this one. That's it. And RZ is mg. Yeah, the third equation. So what did they ask us for? What did they ask us for? I already forgot. Aha, express t and r as a function of time. Easy. Aha, so we already found t from the first expression. T is equal to, so t as a function of time is equal to m L0 minus omega b t omega squared. They didn't give us values. Yeah, this is symbolic solution. Answer part A. Answer A. And our R, our reaction force, is equal to r theta squared plus rz squared. Yep, so that will be equal to 4m squared omega squared b squared omega squared plus m squared g squared squared. I think we can pull something in front of the square root. M, exactly. So r will be equal to m and square root of g squared plus 4 omega squared b squared omega squared. Exactly. This is our answer B. The end of the problem. Questions? Okay, guys. So we have 3 more minutes. And I just would like to show you that there is like steps you should follow, yes? In these problems, yes? So for example, I'm not sure, maybe on the exam, if you see such problem, what you should start with? FBD, yes? I'm gonna write it down, okay? So this is a recipe. First part, FBD plus KD, yeah? And choose coordinate system, okay? Second part, EOM, okay? Then third part, count number of equations and number of unknowns, okay? Number of %99% of the time, you will end up with more unknowns than equations. Yes, 99% of the time, you will end up with more unknowns than equations. So, 4 parts should be look for more equations. Yeah, find more equations. And where should you look for them? For example, friction. Yes, for example, friction equation. Yes. If there is friction in the system. For example, in example number 2, there was no friction. Yes. And what is the other way? Yeah, John? Yeah, kinematic constraint. Yeah, kinematic constraint, geometry, yes, kinematic constraint. Yeah, for example, rope. Yeah, so rope will give us relation between 2 accelerations, for example, yes, of body A and body B. Yeah, and fifth step is algebra. Just this is where wait a second. This is where dynamics stops. Here, dynamics stops here. Dynamics stops here, and algebra starts. So fifth point on our list is algebra. I need 10 more seconds, guys. Okay. Algebra. Just make sure that you don't make like any mistake. But even if you make a mistake, I usually don't take points off. Yeah. What I care on the exam is this. But I'm not grading this semester. Yeah. Okay, guys. Sounds like easy points on the exam. Sounds like easy points. Yes. Follow that recipe and you are good. Enjoy your afternoon. Bye bye. Yeah.